The objective of this lab is to find the mass of an object, in this case a black hole, by analyzing the motion of its surrounding bodies. This is done by utilizing two fundamental principles in particular: the momentum principle, also known as Newton's second law, and Newton's second law of universal gravitation. The numerical results were that the net force was calculated to be 1.367 times 10 to the 27 newtons. The parallel component of the net force is equal to 2.253 times 10 to the 26 newtons. The perpendicular component of the net force is equal to 1.348 times 10 to the second newtons, and the mass of the black hole was calculated to be 3.98 times 10 to the 31 kilograms. So one of the assumptions that had to be made was that the net force was equal to the gravitational force of the black hole upon the star itself. And the two equations that were utilized was Newton's second law, which was defined to be that the change in momentum over the change in time is equal to its parallel and perpendicular components, which is then equal to the parallel and perpendicular components of the net force, which is equal to the net force as a whole. And the second equation utilized was Newton's law of gravitation, which states that the magnitude of gravity is defined to be Newton's gravitational constant times the mass of the black hole times the mass of the star divided by the magnitude of the displacement squared. So then to calculate the mass of the black hole, one has to algebraically manipulate the system, which defines the mass of the black hole to be equal to the magnitude of the gravitational force times the magnitude of the displacement squared over the Newton's gravitational constant times the mass of the star. So the whole process is that VPython code will read in data corresponding to the object's location from a spreadsheet. Then the code will trace the motion of the object given the initial conditions to find the net force. So the initial conditions of the code were that this mass of the star was defined to be 1.989 times 10 to the 30th kilograms, and the position of the black hole in the x direction was defined to be -5 times 10 to the 10 meters, and in the y direction defined to be 5 times 10 to the 10 meters. And the time step, or delta t, is equal to 86,400 seconds. So the principles that need to be defined, or at least some of the variables that need to be defined to execute these principles, was that the initial velocity, or the initial momentum, is equal to the star's mass times the initial velocity, and the final momentum is equal to the star's mass times the velocity final. And then you can define delta v and delta p to be equal to, respectively, the velocity final minus the velocity initial, and the final momentum minus the initial momentum. So in the iterative loop, the change in momentum over the change in time is equal to the change, or at least dp dt is equal to the change in momentum divided by the time step, and then the net force is defined to be this as well. And then the unit vector of momentum is equal to the vector of the initial momentum divided by the magnitude of the initial momentum. And then the magnitude of the change in momentum over the change in time is equal to the magnitude of the final momentum minus the magnitude of the initial momentum divided by the time step. And then the change in momentum over the change in time in the parallel direction is equal to the change in momentum over the change in time, its magnitude, times the unit vector. And then we can calculate the parallel and perpendicular components of the net force utilizing this relation shown earlier. And then we could finally calculate the black hole's mass by then defining G equal to be 6.67 times 10 to the -11th, and then we can plug that in, and then we define the mass to be the magnitude of the net force times the magnitude of the star's position minus the black hole's position squared, divided by the Newton's gravitational constant times the star's mass. And then we can plug that into VPython to get our results. And now I'm going to run the whole code for you so you can see the video. As you can see, the arrows represent the perpendicular and parallel components of the force, and then you also have the net force always pointing to the center. So here's some response questions. So the what if question, or the what is a mean question, is defined to be what is the relationship between dp dt and the f net and its components. So although the momentum principle tells us that these two vectors are equal to each other, the power of the momentum principle comes from the fact that it links two very different kinds of things. If you know the net force, you know how the momentum will change, and you could update the momentum. If, on the other hand, you observe the motion of an object and measure how its momentum is changing, you know what the net force must be acting on the object. In summary, momentum change is caused by net force. And the what if question: what if the black hole we analyzed was replaced with a new black hole of unknown mass, but the motion remained the same? If the black hole whose mass was found to be removed and a different black hole was placed in the same location and the motion of the observed star remains unchanged, then the mass of the new black hole is the same and is the same as the mass of the old one. If the positions stay the same, that means the net force is the same, and by extension, the mass of the new black hole.